Hey guys, welcome to your favorite channel, Subhra the Geek. I am your host, I am your host, Subhra. So today we are on another video of our statistics series, the seventh video. That is the hypothesis testing part 1, which Debayan is gonna explain in very minute details. So guys, these are the videos which I, along with my very great friend Debayan, have planned for you guys. These are the series which cater to the needs of the industry and to all the things that the industry wants. Not in larger details, but in a smaller part. So, guys, if you want to support us, please give a like, please share the video with your friends, and please do comment. Or if you have any suggestions, we have our exclusive Discord server ready. You can join over there and you can connect with us, me and Debayan over there. And our details are also given down below. So, guys, today we'll be learning about hypothesis testing. So, I am your host, Shubro. Along with me is.
Debayan.
Let's start, shall we? So Debayan, today we are going to talk about hypothesis testing, the first part. Could you give our audience a brief about it so that they can understand which are the things they need about hypothesis testing?
So when people start studying about hypothesis testing in their standard reference books, most of them are pretty confused by what people are trying to do in this technique, right? They get confused about the interpretations of a p-value. They get confused about where do I use one-sided, two-sided, and like even the whole general premise of what do you use and how do you use hypothesis testing for. People confuse those, and we are trying, and I will be trying to sort of at least address some of them by being very precise in how the language that I'm trying to use to explain them. I'm not going to use fancy formulas or stuff like that. I'm just going to use normal, simple layman English language to give you the interpretation of the language statement phrases that you should use when you're talking about hypothesis testing. So that's what we're going to explore today.
Yeah, that's a very good thing, the ban which you said, like not the formulas and all. It's in the layman's English term, so that all of our audience who are not from a mathematics background can also understand and have a great knowledge about hypothesis testing and make sure that they can crack the sexiest job of 21st century of Harvard, as per Harvard Business School.
And to add to that,
Yeah.
it's more about it's not that I'm trying to use normal simple English to
Mm-hmm.
explain to you. Obviously, that's one of the reasons. The other reason is if you cannot explain what you're trying to do with hypothesis testing in a real life use case scenario to your stakeholders, to the business executives, to the business owners, right? You have not done your job. You as a data scientist, as a data analyst, you're responsible for communicating complex mathematical statements to simple people so that they can take actions on what you just said. In order to do that, they need to understand the baseline, the implications of that in simple language, and so that the language that I will be using today in our explanations should make direct relevance to what you're going to say to the stakeholders in a real life scenario.
So let's jump onto the band's tab where you'll be explaining each and everything in minute details. So the
Hmm.
band, let's go over there.
Okay. So hi guys. So let's start with first defining some terms when you come across hypothesis testing, or when you're going to start something related to testing or A/B testing, for example, right? You need to understand hypothesis testing before you go on to that. Before we do that, I want to lay some groundwork, some vocab, if you mean, in this field that we use. Let's start with the two most misunderstood words, right? Let's start with theory and let's start with hypothesis. Right. In your normal everyday language, when you say that I have a theory that something's gonna work out, or when you use the word when you use the word theory, right, in everyday language, it's most of the times, or majority of the times, I would say, is incorrect, right? Theory is not what you think it means, and in actuality, the way that you use theory is actually you should use hypothesis in that context, right? For example, when you try to say that you have an idea, you have a theory of some working idea, some working principle behind something, or you expect or suspect something's going to happen, that's a hypothesis. You do not know if that's true or false. You do not know anything about that statement. You have some information, but you do not have complete information to make a statement about that event or that scenario. So what you should be really saying is that you have an hypothesis and of something happening, or you have a guess or something, and that's it. That's the end of it. A theory is something, or it's something that has been repeatedly tested and cannot be disproven. That means the evidence all piles in favor of the hypothesis and not against it. If you find just one instance of an evidence that stands against the theory will be again converted back into a hypothesis to be proven again, right? So a hypothesis becomes a theory, and that is after a lot of evidence, after a lot of evidence and experiments. So you cannot just simply discredit a real theory. So the all scientific theories are real theories. They might be incomplete. So you can say that Newton's theory is incomplete for gravity, and Einstein's theory is a replacement or an upgrade to Newton's theory of gravity. But you cannot say that Newton's theory is wrong. It's not wrong, it's just that it's incomplete. A theory is meant to be a hypothesis that has been repeatedly proven. Newton gave some hypothesis for his theory of gravity, and we have seen them happen, so that's why it's a theory. That's it. That's all it there is to is. uh, Now, based on this context, on the context that I've established right now between the difference between theory and hypothesis, the way that hypothesis, like starts off, is like, how do you know how to create an hypothesis? That's a great challenge. You need to know how to create a good hypothesis to even start testing and forming into a theory. So the way that we do that is using something called a null hypothesis and an alternate hypothesis. So null hypothesis, let me write it down. A null hypothesis is denoted by the symbol H naught. That's a subscript over there. And the other thing that I was talking about is the alternate hypothesis. I think the names are pretty obvious, what they try to mean, but in case you didn't understand, a null hypothesis is your default state. It's a claim that you wish to test. Is the idea that you wish to test and prove or disprove, right? So this is the claim. For example, you want to say, the Earth is flat, right? That's your null hypothesis, right? You're making a claim, and that claim is put up for testing, and you're gonna pitch all the evidence in favor or against the null hypothesis. The alternate hypothesis is what is against or rebelling against the null hypothesis. This is your opposite, or not opposite, but the alternative one, the other answer for the claim. If the null hypothesis is false, then what you're going to look forwards to, you're not going to turn to, you're going to look forwards to this, right? So the alternate claim, this is the alternative claim that you're considering. So whenever you are working with experimentation, you're working with a scientific, like a hypothesis, you should always have a null hypothesis and an alternative hypothesis. Otherwise, you cannot compare. You always compare relative to each other. You're gonna compare. You're gonna test the null hypothesis against the alternate hypothesis and see which one is more compelling to use. Which one is more compelling in terms of the evidence that you collect, right? And in statistics, or in simple data science and machine learning, this can be a parameter of interest, right? So if you say that you have a mean, right? Let's say you have a mean, and you want to say that the mean is definitely more than 7 or something. That's your null hypothesis. That statement becomes your null hypothesis, and then you're going to say that, okay, the alternate hypothesis is that, just a complementary of this, you're going to say that the mean is not more than 7. That's your alternate hypothesis. It's as simple as that. And it doesn't need to be more complicated than that. The alternative hypothesis is always the complementary of your null hypothesis. It's always against or the opposite, generally the opposite side of what your null hypothesis is. And what you're going to do is that you will look at the data. Now, listen to this very carefully. You're going to look at the data. You, the skeptic, right? The skeptic, so this is you, the skeptic will not abandon H naught unless the evidence is in favor of unless the evidence is so strongly favoring the alternate hypothesis that you do not have anything to do, right? Unless the evidence is strongly, we're going to define what strongly means, but just for the sake of a qualitative definition, it's strongly in favor of H naught, right? You're not gonna shift your position. Your default position is always H naught, and you're not gonna shift your position until and unless the evidence or the data that you receive or will be receiving, it strongly suggests that H naught is more likely to be true. You never say that it is true. You just say it's more likely that H naught is true and H naught is false, because you can never definitely claim. It's all relative. Remember, you cannot definitely claim anything in science. You always say that it's more likely H naught, H alternative is true to H naught, given the evidence, given the data, statistical or machine learning that you receive, right? So this is the whole crux of the hypothesis testing. You're gonna repeatedly set up hypothesis like null hypothesis, alternate hypothesis. You're gonna see the data set. You're gonna do some computations on it. You're gonna obtain some metrics out of it. And if the metrics strongly suggest that H naught is more likely, you're gonna say that okay, I reject the null hypothesis in favor of the alternate hypothesis. This is the language that I want you to use. I reject the null hypothesis in favor of the alternate hypothesis, or I cannot reject the null hypothesis in favor of the alternate hypothesis, given the data set that I have got. This is the language that you should always use, and you cannot deviate from this. This is how it's constructed. It's not meant to be definitive, it's meant to advise you in which direction of the experimentation you should go, right? One of the common things or common metrics that we use, or common number that we see, is the p-value, right? The p-value. You must have heard of this, or if you haven't, okay, I'm gonna introduce that to you. The p-value is simply called the probability value, and what this means is that I can summarize it in a more simple language. Is like this. Please be very careful about how you use p-values. So it's like observed. So what's the probability of observing or seeing observed observed a more extreme outcome given that H naught is true, right? So the probability value or the p-value is basically the probability of you having observed a very extreme kind of outcome which is totally against what you know the H naught is claiming, given that you have made the claim or you are very confident that H naught is true, right? So let's say you have done some previous experimentations. Let's say you got that your H naught is that mu is equal to more than 7. Let's take the same example, right? And then you did some previous test. You saw that okay, I'm not going to reject the null hypothesis because I do not find evidence to be strongly in favor of the alternative hypothesis. Okay, that's it. So you're saying that okay, let's assume that mu is actually more than 7. You're assuming that H naught is equal to true, right? But then you do another experimentation, and then you find that you found some values or some approximate values of mean, we strongly suggest that it is more than 7. It's definitely 9 or 10 or something, right? It's there, but you didn't see it earlier. This is how real life works. You get more data, and then you update what you thought or what you had, what your opinions were, right? So you got new data, and then you saw that maybe the mu is not is definitely definitely sorry, less than 7, definitely not more than 7, but definitely less than 7 or equal to 7, right? So what are you going to do about it? You're going to see the probability of obtaining a value which is less than 7, mu less than 7, given that you know that, or you assume that mu is more than 7, right? You're going to look at the probability, and if that probability is above a certain threshold, or some percentage of probability, you're going to say, okay, I think I'm going to turn back, I think I'm going to reject the null hypothesis. So this is how the p-value works. You make a null hypothesis. You say that you look at the probability of getting a more extreme or a more adversarial outcome or observation, given that your assumption is already settled that h naught is, some statement like mu more than 7. What is the probability that you will get mu is less than equal to 7, given that you have already got a conclusive idea from previous experimentations that mu is more than 7? You saw that it's pretty high. It may be 10%, maybe, I don't know, 15%, maybe, 7%, 5%, some value, some percentage value. What's your threshold? How much evidence, how much convincing do you need to do, or you need to get in order to change your mind? That's your thresholding, and that thresholding is what we call the significance level. You see how the language comes in. If you know this, you will see how the whole context sort of comes along. If you do not know this, now let's learn from the basics then, right? Then you have a significance value called this is the significance value. Generally, it's in the range of 1%, 5%, and 10%, maybe really in certain cases. Medical data or medical hypothesis or testings generally work with 1% and 5%. The vaccines, I believe, if they use p-test, I don't know if they use p-test for covid-19, but definitely they would be using something along the lines of 1%, or less than, even more stronger than that, less than 1%, right? If they find anything abnormal about the vaccine, they're going to reject the null hypothesis that the vaccine is okay, right? This is how you define whether how you work with an hypothesis, right? So let's work through an example. Let's work through an example, a real life example. I'm not going to the next page. I'm going to use a different link for this time. So let's say you have a data point, right? So let's say your p-value. I'm giving you the p-value. Let's understand the example I'm trying to put over here. So you want to find out the probability of your mean more than 3.2, for example. This is one value, right? And given that your null hypothesis is that mu is equal to 3, it can be, right? You did some previous experimentations, you found that your mu is equal to 3, and you're pretty confident about it, but now you're going to find out, okay, I got some values around 3.2. Where I wrong in my previous hypothesis, in my previous experimentations? So what's the probability that the new mean with the new data as it comes along is more than 3.2, right? So that's the probability value. That's how the language is going to look like. Now let's say the data, right? This mean value itself, the variations in the mean value is normally distributed. Please understand this very carefully. You do not know what the actual mean is, right? That's why it's X bar. You do not know what the sample mean is. You have done multiple iterations, experimentations, and every time you get a different value, but around some neighborhood, some range, right? That value comes along, and let that range be a normal distribution. I'm gonna represent as a normal distribution, whose mean is 3. It's around 3. I know it's something around 3, and the standard deviation or the standard error, standard deviation is 0.246. I'm taking this from a book. So mu is 3, AC is standard deviation is 0.246, and your mean is somewhere along this normal distribution. It always goes along this normal distribution. Let's say you do 50 trials. You did 50 experimentations before, right? So what do you get? What do you find over here? Your experimentation is going to look something like this. Your values that you get, right? So your mu is equal to 3 over here. We expect that this is true, right? You've seen this propping up multiple times. Then you're going to look at this value, right? And this value is equal to 3.2. It's right on the right hand side, right? So obviously this whole range is going to be all values which are more than 3.2, right? And remember, this is a normal graph that you drew. So that is basically the probability density curve, and this shaded region This shaded region that it do is basically it is the if you find the area of this of the area under this curve, you're gonna get the probability or the p-value that the x is more than 3.2, given that your null hypothesis is mu is equal to 3. So this is how you're gonna get it from a normal distribution, right? So how do you do that? You're gonna compute the z value. Simple as that. You're working in normal distribution, go with the z value, right? So what's the z value at x bar is equal to 3.2 when you know that x belongs to a normal distribution of 3 and 0.246. When you know this is true, how do you do that? You basically subtract the value from the mean and divide it by the standard deviation. How many standard deviations is it away from the center? How deviated it is? How much error is it? How many errors are there in that value? I found the value to be approximately equal to 0.81. Right. So this is your metric. This is the test statistic. This is the z score of the probability, or sorry, the z score that x bar is more than 3.2. Right. How do you find the probability? You can either do the area under the curve, or you can do something in Python or R. You're gonna find the p norm. Right. P norm function. P norm function. Right. What are you going to do for z, or you can look up the z table if you have one nearby, if you have a maths book nearby. For z more than 0.81, right, or z or x bar more than 3.2, they both mean the same now. So for z more than 0.81, the probability of z getting more than 8.81, or the p-value, is basically equal to 0.209, this value, right? What does it mean? What did I write just now? Right, it means that when for p, or the probability is equal to 0.209, sorry, it is 0.209, yes, there is a let me write this down for you. There is a 20.9% chance that x bar was actually 3.2 or more than 3.2. You can see how the language changes, right? How we use the language over here. What did it first do? We found out, okay, what the range values are. We created a normal distribution of the values from, for which I got the observed value, which is the mean. How the deviation in the mean happens, the actual value of mean happens. I represented that using another normal distribution where the median, sorry, the mean of that of that values is where my null hypothesis is. And then I'm checking using z value how deviated it is from my expectations, from my null hypothesis. And then I find out that there's a 20.9% chance that the mean is actually more than 3.2, right? So this is the probability value. Now it comes down to you. It comes down to you. Do you accept that this is a high chance? Is this high chance relative to you? How do you define high? It depends on you. Do you define 5% too high? Do you depend 10% too high? Do you think 25% is too high? How do you define high? It depends on you. That's your significance level. Someone will either define it for you based on the experimentation or the sensitivity of the experimentation, how precise you need to be, how much error you can allow for it, right? Or you can define it yourself, right? So the probability of observing data at least favorable to our current data set, if H naught is true, that's the another definition. But let's stick with a simpler one. The probability of observing more extreme examples, given that you know H naught is true, or you have seen repeatedly that H naught is more likely to be true. What does the new data tell us about this? That's the p-value. The p-value tells me there is a 20.9% chance that x bar might be actually more than 3.2, and your previous hypothesis that x is around 3 might be wrong. I know you agreed it in previous experimentations based on the data that you received then, but given the new data that you got now, maybe it was wrong. Maybe you do not know, but there's a 20.9% chance that you are wrong, right? So the significance level. So if I say the significance level alpha is 15%, then definitely I'm going to accept this. I'm going to say that, okay, definitely I was wrong. My null hypothesis that the mean is equal to 3 is wrong. If my x bar is 20%, I'm still gonna say, because it's more than that, right? I'm still gonna say that I was wrong. If my x bar is 30%, I'm not gonna reject the null hypothesis. So it all depends down on how sensitive do you want your probability to be. When do you know when to cut off? When do you know when to stop? That depends on you or the experimentation or someone who defines it for you, right? So so that's it. You might have noticed, like the more observant ones over there, you might have noticed that when I did this graph, when I did this problem, and then I shaded this part, right? I shaded the right side part of it. What about the left side? You could do the left side as well. It didn't make sense because I'm talking about x is more than 3.2, right? It didn't make sense. But in case we have a scenario where your null hypothesis has like more than and less than equal to both of them at the same time, you have some test where it includes both sides as well, left hand side less than some value and more than some value, right? Then you would use something called the two-sided hypothesis test. This is a one-sided one. What does it mean? It means I'm just working with one side. Either it's more than something or it's less than something. And I'm going to work on that p value and z score, right? If you need both of them, then you're going to do a two test or two-tailed hypothesis test. This is a one test. Is there anything new about it? No, it's just the same as before. You're going to look at the total probability or the p value that you get under both of those sides. You're going to add them up. You're going to get a total probability, and then you're going to work with that, right? So if you have a scenario, let's say, let me look out the values. Okay, so let's say there's a probability that you're working with a probability value where x bar is more than 3.2 or x bar is less than 2.8. It can be either of them. You do not know, right? Given that your previous hypothesis tells you that mu is equal to 3, you could do both of them, right? And what do you do from both of them? You find out the z score for both of them. For both of those sides, you mark another region over here. You find out the z score for the first one or the second one as well. You're gonna get a range of z score which gonna be like around 0 minus 0.209 and 0.209. You're gonna get this value when you calculate the z score. These are the z score range. That means your probability value should lie between these two. So what does it mean? It means that you're gonna find out the total probability by z is more than a 0.81, right? or you add them and then you find out what is the probability that z is less than 0.81. Either way, you need to find out the total probability from both tails of the hypothesis, right? And this is same as just multiplying. It's going to be the same value. The normal distribution is symmetric on both sides when you work with an ideal case, so it's going to be same over here. And then this is effectively equal to just double of more than 0.21, and that is equal to 0.418 or 41.8%. That's pretty high. That's pretty high. So you can see that as you increase the range of your possibilities, obviously the probability is going to go high, right? That's how probabilities work. You increase the search space, you increase the sample space, and the chances of you getting the right result increases. That's pretty common sense, and that's why you see it double from 20.9 it's now 14 or 41.8, right? So in a double-sided test, now you have to decide, okay, what's my significance level, right? If is it 50%, is it 30%? You have to decide when do you accept. If alpha is 50%, you do not reject your null hypothesis. If alpha is 30%, then you definitely reject your null hypothesis in favor of the alternate hypothesis, right? So that's what it is. It's as simple as that. Now we're going to talk about something that we're going to talk about errors. We're going to talk about the kind of mistakes that you make in hypothesis testing, and it's so common that people actually have a name for it. And you might have heard this in machine learning, like when you were doing confusion matrices, when you were doing those kind of things, you must have heard about true positives, false positives, and those kind of things, right? Those actually come from this kind of error or types of errors that we're going to discuss. It's an extension of the hypothesis testing or the kind of errors that you get in during hypothesis testing, and it's so common, and even people do it as well. Doctors, people, everyone do it on a common basis. It's so easy to make that mistake, and that mistake is what you would call type 1 or type 2 errors. If you're a statistician student, you might have heard about this. If you're a computer science student looking into data science, machine learning, you might not have heard about this, but it's simply called false positives and false negatives, and it comes along with the confusion matrix. The two sides. The If you have a confusion matrix, right? So this side and this side. So this one is a type 1 error, this one is a type 2 error. If you that's a confusion matrix. First, coming down to the context at hand. When it comes to hypothesis testing errors, right? So it's like this. You create a table, right? It's very similar, but you create. You say that you make your decisions. What are the decisions you can take, right? See, so the truth. Let the truth be heard. So this is the truth axis. So this is where the actual result is. H naught is true. Let's see that the claim or the null hypothesis is actually true. You do not know it's true, but it's just that it's actually true, right? You do not know. I'm just making the assumption that maybe this is the truth, and you do not know. Then what do you do in light of that? Uh, and the alternate say H naught is also true. On the other side, on the x on the top, right? This is where your predictions come in. Your predictions come in. You're gonna say that you fail to reject the null hypothesis, or you rejected the null hypothesis. It can either be on those cases. Please note that I'm not writing that I am accepting an alternate hypothesis. You never accept an alternate hypothesis totally. You simply decide on your current stance. You never propose alternate hypothesis. You propose a null hypothesis. That's your default state. The alternate hypothesis there can be many number of alternate hypotheses, right? It can be anything that's complementary of the null hypothesis, just opposite against the null hypothesis, right? So you could have millions of alternate hypotheses, but you have one null hypothesis, and you're going to make your decisions based on whether the evidence points in favor or against the null hypothesis. So that's why I've written either you fail to reject it, or you rejected it, right? If the null hypothesis is true and you fail to reject the null hypothesis, that means you made the right decision. Good, you did the right thing over here. If the alternate hypothesis is true and you rejected the null hypothesis, that is also good. You did the right thing here as well. But if the null hypothesis is true, but you rejected it for some reason, maybe if faulty data set, or you made a judgment call, a bad judgment call, then that's an error. This is an error. And the same is true that if the alternate hypothesis is true, and you actually fail to reject the null hypothesis, that means you're sticking with the null hypothesis. That's also wrong, right? That also bad the judgment call due to any reason, right? So in both of these cases, it's an error. We have special names for these errors. This one. It's a type 1 error. It's a type 1 error. This one is a type 2 error. So you generally reject. So if when the significance level is lambda, right? Sorry, is alpha, right? You reject the null hypothesis when the probability value is less than the significance level, the alpha, right? So this implies that when the null hypothesis is actually true, you do not want to reject more than alpha of times, right? So there has to be a certain number of times you want to repeat that experiment and see that you're actually right. You're actually in the right direction, but there can be errors. There can be errors in either of those cases, and you have to constantly check whether the judgment call that you made based on the experimentation you did now with the data that you have now is correct, right? So you can see the kind of mentality that you have, and for a very good example, if you're talking about the COVID-19 vaccines, if you think that the doctors are too finicky about what they're trying to say, and they are changing their decisions every now and then, it's because of this. With the data that they come in, they look at it, they update their hypothesis, and they're going to say, okay, my null hypothesis of the vaccine was working. I have not seen any. I have seen new virus mutants that say that, okay, it's against what I knew. I'm going to update my hypothesis. I'm going to say that, okay, this vaccine might not work, or this vaccine actually works because I saw that even the new mutants cannot affect the vaccine strain that we have done, right? So in either of those cases, this is the framework that they might not be using the exact thing. They might have more sophisticated tools. They're not going to leave it down to a couple of p-tests to decide your life on, right? But they're going to do more tests. But it all comes down to the framework that we're using over here. It comes down to whether do you accept the likelihood of you being wrong or right, and how wrong, or what does the data tell you? As the data comes along, you're going to update your hypothesis. You're going to tell, okay, I was more wrong, I was less wrong, and that's it. You can only talk in terms of how wrong you are or how likely the chance is. You can never say you're right. That is not how we work in hypothesis testing.